Hello, everyone. So let's start our lecture. Today, we're going to talk about monopole antenna. So this would be the topic of this lecture. And if I have some time, I'm going to start loop antenna as well. So you see, with dipole antenna, we essentially have two arms to create our radiation. This is somehow similar to the two hands when you create acoustic waves. For example, you can create acoustic waves using that. But then in some applications, you might want to potentially remove one of the arm. So this would bring you to the concept of monopole antenna. So I'm removing this one, and then this makes it monopole antenna. But monopole antenna doesn't work just by itself. You essentially need what we call a ground plane. So a metallic plane beneath that. So this would be your monopole antenna, and that you're going to have a ground plane. So if I want to maybe plot that, that would be a metallic plane. I call it perfect electric conductor in the ideal case, perfect electric conductor plane, or you may call it ground plane. That's a metallic plane, and the antenna would be above that. So in this case, this would be your source connected to this. Now, this would be essentially your source. Now, if I want to show you a monopole antenna, this is the monopole antenna that you're going to see in the videos of the lab. So this is just one arm, as you see. This is only one arm, and this is the metallic plane. So, or ground plane. In my discussion today, I'm assuming that this goes to infinity. But to go to infinity, you really don't need to go to infinity. You need to be large with respect to wavelengths. So for example, if you are 10 lambda, it's relatively large, and 10 lambda might be very small depending on the frequency. For example, if you are at 10 gigahertz, then the wavelength is 3 centimeters. So 10 lambda would be 30 centimeters. So this is essentially one arm, and this is the ground plane. And then we're going to be studying this type of antenna. And then we feed the antenna from here, and then that would be our monopole antenna. You're going to see that later on in the labs. So this is my monopole antenna, and so if I think of generating acoustic waves with two hands, I could, for example, use one hand, like one arm, and then use a plane. So they, in conjunction with each other, they can create acoustic waves like that. So this is, it's not a one-to-one correspondence, of course, but you get the idea that we can use one arm to actually do a similar job to a dipole. Now, before talking more, let's see what is the basic of this in terms of operation. Why just one arm would work? The operation is based on something called image theory. So image theory essentially says that if you have a PEC plane, ground plane, and you have a current like that above the PEC plane, a piece of current above that, so let's say it is at height h above the PEC plane. Now, if you want to analyze this structure, the analysis of this structure can be complicated because this antenna is operating close to a PEC. So what would you do? So the reason it's going to be difficult is that this is in proximity to PEC. So if I can remove the PEC somehow, then the analysis would be much easier. Now, how would you remove the PEC? So what you do is that you create an image of this. So this is H, so you go H here, and then you're gonna have a current in the same direction, same size. So this would be the image of that. Now, you can remove the PEC plane. I'm just gonna keep a contour of the PEC plane so that you see the location of the PEC plane. So now this system, which is two antenna, but now it is in free space, there is no PEC anymore, would generate identical radiation above the PEC plane. So above here, so on this plane, it would generate identical result to the case that you had a PEC and then you had just one current. So above here, these two systems are equivalent. This system is easier to analyze because there is no PEC. I removed the PEC. But this system is more complicated because you now have a PEC. Now, what about below? So below here, of course, you get something which is going to be similar to what you get above. But here, because PEC shields this environment, no radiation gets to PEC. So you essentially have nothing here. So there are no fields there because everything that's going to hit the PEC is going to reflect back. So it's 100% reflection. Nothing is going to make it. And in fact, it's because of this reflection that you may think of this reflection that's coming from the image of the current. So that's essentially the mechanism of image theory, that if you have, because of this reflection, you may think that reflection comes from that, and then you remove the PEC. So that means if you have a vertical current with respect to PEC, you can remove the PEC and keep the image of this current, which would be in the same direction. Now, let me put back the PEC here. Now, if the current is horizontal, then you're going to have, again, an image, but this time, the image would be in the opposite direction. So they would be out of phase. So these are the two important things. If you have vertical current, you get a vertical current in phase. If you have horizontal current, you get a horizontal current out of phase. And if the current is oblique, essentially you can decompose it into two currents, this one and this one, and then you find the image of this one separately, image of this one separately, and then add them together to get the image of the original currents. You can do that as well. So based on this, what we have in monopole antenna, so if this is your monopole antenna, so monopole antenna would be something like this. You have a current like that close to the PEC, and you have perhaps a source here that excites this with respect to the PEC. So you can essentially assume that there is no PEC. So you're going to have the image of this current, and you also have a source which is here. So you can remove the PEC essentially like that and model your antenna, monopole antenna, as a dipole antenna. So your monopole antenna becomes exactly like dipole with only one major difference. And the major difference is when you are dealing with a monopole antenna, so if this is your monopole antenna, you have radiation only in this region, assuming that this PEC goes to infinity. And here would be zero because PEC is going to shield this environment. So this equivalent model of that is only equivalent with respect to this area, because this equivalent model also radiates in the bottom half of space. But this one, the bottom half of space, is essentially shielded. So this is, you can see a one-to-one correspondence here between this monopole and this dipole that you have there. So that's why we don't really spend much time on monopole, because we can connect it to dipole that we've already learned. Now, there is another thing that's actually you can learn much from that. Forget about monopole for a second, and let's use a dipole antenna. So let's assume that you have a dipole antenna like this. And as you know, dipole antenna has in-phase current if it's, for example, half a wavelength. So let's assume you have an antenna and you have a PEC here. And you want to analyze this antenna system. So you could potentially say, let's remove the PEC and then use the image of this. So the image of this, you have currents horizontal. So the image would be opposite. So now you can remove the PEC. I'm just going to keep a line to tell you this was the PEC. Now you can remove the PEC and assume that everything is in free space, but now you have two antennas. So now you need to you need to plug the two antennas in the equation for A equal J, if you remember, e to the power of minus jk r minus r prime, r minus r prime dv prime. This was r prime, this was r. And then you can find A, and then you can find far field E and H. But then there is one thing here. If this is very close to the PEC plane, if this is very close to the PEC plane, what's going to happen? So let's do that. Let's make it very close. So let's bring it here. Very close. So if it's very close, then the image, of course, would be very close. So as you see, because now I assume that this height is much smaller than wavelengths, these two are so close that they look like a transmission line, that you have current here, current in the reverse direction. So we said there is no radiation from this, because if these two currents, they're very close to each other, they cancel the effect of each other. So that's why if you put a dipole antenna very close to the surface of PEC, essentially you get no radiation. So this is what's very important here, that you shouldn't put a dipole antenna horizontal to a PEC, otherwise you get no radiation. If you want to operate a dipole close to a PEC, perhaps you need to either increase the distance or you need to have it vertical like that, so the image theory helps this, otherwise image theory cancels. If they are farther from each other like that, then the image would be also farther. And because in expression for A, we have J, summation of J, and these weighting factor, because the distances are different, they may contribute to help you. But if they're very close to each other, this has no effect. You just have the summation of J, and they cancel the effect of each other. So this is something that you should keep in mind. So let's now continue with our monopole antenna. So let me remove this, and let me ask you a question, for example, that I want to study. So let me tell you this, that let's assume that this is my question, that I have a monopole antenna, and the length of monopole antenna is lambda by 4, and I want to know what is input impedance of this lambda by 4 monopole. This is my question. So what would be the input impedance of lambda by 4? So the input impedance is the impedance seen from here. So what would you do? You would say, okay, this is equivalent to a dipole antenna based on image theory. And now I know the Z in of dipole antenna, and because this was lambda by 4, then my dipole antenna is half a wavelength, because lambda by 4, you have 2 of them, it becomes half a wavelength. So this is the corresponding dipole antenna for that. So what is Z in of half a wavelength dipole antenna? It's about 73 plus J 42.5. But we've learned that if we cut it a little bit, maybe make it 0.48 lambda instead of 0.5 lambda, this would be gone. So let's assume that we already done that, and this is like that, and the same thing here. So the same amount that we cut from here, we also cut from here, so that we have this one-to-one correspondence. So this is Z in our half a wavelength dipole. It's not exactly half, it's a little bit small. So now what would be this Z in based on that? Now, based on image theory, if you have a voltage source here that derives this, then if you make it 2 arm, so essentially you have 2 of those voltage sources. So, but this current here would be the same as this current here. So Z in is V of monopole divided by I of monopole. But then I of monopole, I right at the excitation port is the same as I dipole. But V of monopole is half of V of dipole when you make it a dipole. So this is half of V dipole. And you know that V dipole divided by I dipole is Z dipole. So Z of monopole becomes half of Z dipole. So that brings me to the conclusion that if this is 73, Z in of quarter wavelengths becomes 73 divided by 2, which is about 36.5 ohm. So this is the relation between the impedances of monopole antenna and its corresponding dipole antenna. Now, if I, for example, tell you this is the input impedance of a dipole antenna, find the input impedance of the corresponding monopole antenna, you can do that. Another example would be for full wavelength dipole antenna. So remember, if you have a dipole antenna, which is 1 lambda, so this is a lambda dipole, then the corresponding monopole would be, you have a PEC plane, and then this would be your monopole, and the size of monopole would be half a wavelength. So in that case, what would be the Z in of the half a wavelength monopole? So if you remember, so I shouldn't plot it like that, the current distribution was like this for full wavelength dipole. Z in of full wavelength dipole would go to infinity, becomes very large because current goes to 0 at the input port. Therefore, Z in of half a wavelength monopole should be half of this, but because this is already very large, this one also goes to infinity. And this is exactly what you expect, because if this is the current distribution of full wavelength dipole, the current distribution of half a wavelength monopole becomes essentially this. So just to here, and then you see current goes to 0, therefore input impedance goes to infinity. It still goes to infinity. And if you look at the current distribution of half a wavelength dipole, this is like that. And if you plot it for quarter wavelength monopole, it would be like this. So this is now the appropriate one. So what was the conclusion for dipole antenna? That half a wavelength dipole antenna is a fantastic antenna. So therefore, correspondingly, quarter wavelength monopole would be a fantastic monopole. But you just need to cut a little bit of that to be a slightly less than quarter wavelengths lambda, quarter wavelengths, or lambda by 4. So this is the discussion on Z in. Now let's discuss, for example, directivity. So let's discuss our directivity. So let me plot this again. So again, I'm gonna ask a question that, let's say I have this monopole antenna. So this is, let's say, the source that drives that. And I'm assuming that this is quarter wavelength. You see, this part is just the excitation gap is so tiny. But because I want to show the voltage source, I a little bit emphasize that. So this should be extremely tiny. So this is my question. What is the directivity? So, or call it maximum directivity of quarter wavelengths monopole? That's the question. What's that? What's the maximum directivity? Then you would say, okay, I know that this is equivalent to a dipole. Right now, the dipole is going to have 2 of these voltage sources. Because based on image, you're going to have another voltage source, and then you have that. And remember, this equivalence is just above here. So this system and this system are equivalent here, but below they're not equivalent because you have radiation here, but you have shielding here. Now, let me write down the directivity of half a wavelength dipole antenna. So directivity of half a wavelength dipole antenna 1.64, or in terms of dB, we're looking at 2.15 dB. That's the directivity of our half a wavelength dipole. 1.64 dimensionless, 2.15 dB. Now, how do you decide on the directivity here? So what would be the directivity here? Let's write down the equation for directivity. Equation for directivity says that directivity is radiation intensity divided by radiation intensity of an isotropic antenna, assuming that the actual antenna and isotropic antenna have the same radiated power. So the radiation intensity of isotropic is the total radiated power P rad, equally distributed over the whole solid angle, which is 4 pi. Therefore, it becomes 4 pi u theta phi P rad. So this is essentially what we have for directivity. And if I want D naught, which is maximum, this would be U max. So that's the equation for directivity. So I need to use that to figure out the connection between the directivity of these two. So to do that, let's write it here, that D naught of monopole is equal to 4 pi U max of monopole divided by P rad of monopole. Now, what is U max of monopole? Let's first look at U max of dipole. So this is the radiation pattern of dipole, of course. So what is the maximum of U? It happens here or here at theta equal 90, assuming that this is your Z axis. So now what would be the pattern of monopole? So it's going to be exactly like that. Above here, they're the same. So this would be the pattern. But then it stops here, right? So because below, it's PEC going to infinity. So essentially, it stops here. There is no radiation here. But if you look at the max, this one and this one, they need to be same because they are still above the PEC plane. So this U max and this U max, they would be the same. So I can just say 4 pi U max of dipole instead of U max of monopole. But then what about P rad monopole? So P rad monopole is essentially half of P rad dipole, because look at that. You have one source here. Now you have two sources here. So essentially you get half of total power. You can look at it from a different point of view. This radiates only in the top half a space. This radiates in the top half a space and bottom half a space. So the total radiated power for monopole is half of that of dipole. So if you go by that, you know that this is essentially going to be a D max of dipole, D naught. So, and then half can go to the numerator and becomes 2 D naught of, so hopefully I've done everything correctly, 2 D naught of dipole. So D naught monopole would be 2 times D naught of dipole. So whatever the directivity of half a wavelength would be, the directivity of monopole would be 2 times that. Not because it's more directive, I mean, it is more directive, but know the reason. The reason is we assume that there is no radiation in this bottom half a space. That's the reason here. So the size of the antenna in the top half a space is the same as the size of the antenna in the top half a space, But here you assume no radiation, so essentially in terms of Prad, you were less, and that helped the directivity value. So if I go by this, the half a wavelength dipole is 1.64, then D of monopole becomes 2 times 1.64, which would be 3.28 dimensionless. Now, what about dB? If you have 2.15 dB and you say 2 times something in dB, 2 times something would be 3 dB more. So instead of 2.15 dB, you can just add 3 dB to that, which would be 5.15 dB. That would be the directivity of quarter wavelengths monopole antenna. And the same argument now can be used for half power beamwidths. Now, the half power beamwidths of this antenna would be, I did it in a bad way, but this is 78 degrees essentially for half a wavelength dipole antenna. Now, if you do that, this point is essentially the same as that, this point is the same as that, so you still get the same point, but then you don't have anything here. So now your half power beamwidth in this case would be 78 degree divided by 2. That would be half power beamwidth of your monopole antenna. So if I want to make a couple more examples, for example, you can consider the directivity of 3 lambda divided by 2 dipole antenna, which is a 2.3. And if you go by 3 lambda by 4 monopole antenna, it would be 4.6. So these examples that we have here, you can do it for other antennas, and that would be in my course notes. So please check them. So that brings us to essentially our conclusion about monopole, which you can think of it as a dipole antenna, but above the PEC plane, assuming that your PEC plane is large or theoretically goes to infinity. Then you have a relation between directivity of monopole and dipole. You also have a relation for the input impedance of your monopole with respect to input impedance of your dipole antenna. So you would have both of these things. So one other thing that I want to mention at this point that relates to both dipole and I'm not going to go to the details of that. I'd like to ask you to check the course note. But remember, if I have a dipole antenna, one thing that I always said is that this is the current distribution if it's half a wavelength. So the current here is essentially the same as current as on the other arm. So this is because I use 2-wire transmission line to bring the current to this system. If you use coaxial cable, so then you're going to solder another arm here, and another would be you have another point here. Now imagine that this current, which is on the inner conductor, you give it to this. So this is the current on the inner conductor I that goes here. But then the other current, which is the current on this one. So if you have a current on this one, then the current on this one has 2 options essentially. So if I perhaps plot it like this, it would be better. So this is one current here, this is the other one. So, and then the current on the outer conductor has 2 options. It goes here or comes back here. So if the situation like this happens, then the currents on this conductor and the current on this conductor won't be exactly the same. So the system won't be balanced like this. Because if you have a 2-wire system, it's a balanced system. The current here, they have nowhere to go except 2 arms. But if the current has other options, then you might get exactly the same current. So you may end up with a situation like this, that this current is in fact larger than the other current. Now, in the course note, we're going to talk about methods to fix this issue, and those methods are called balun. So these are systems that change the unbalanced system to a balanced system. So then you can fix this issue that you have discrepancy between the level of currents. So citations would be in the course notes, and further readings has been provided in the course notes that you can check. So now I'm gonna stop my discussion on monopole antenna and dipole antenna at this point, and then we can move on to our discussion about loop antenna. Okay, let us continue our discussion on the loop antenna. So we talked about dipole antenna and monopole antenna. When we think about dipole antenna, we essentially started with an open-ended transmission line, so it's open circuit, and then we said we're going to evolve that into dipole by bending part of the transmission line. So this is an evolution from open circuit transmission line. So when it comes to loop antenna, the situation is reversed. Now this time this is not open circuit, in fact this is short circuit. So now you take part of that and then you make it. So this is the transmission line, the same as that. Here I emphasized the separation to create my short circuit. But remember, in transmission line, this separation is much smaller than lambda. So then I'm going to open it up. So I take this area and I'm going to open it up and I'm going to make it a loop. So you see, if I want to make a proper plot, then this is my original transmission line. So short circuit here. So you take part of it and then you make it in the form of a loop like this. So this is essentially becomes a loop antenna, and we're going to talk about this antenna. So this is, let me have an example for you. So this is, for example, a coaxial cable. So you have a coaxial cable that comes. So inside coaxial cable, you have essentially two conductors that are very close to each other like that, extremely close. But then to make an antenna, you create separation between them like that to make a loop. And of course, at the end, these two connectors are connected to each other because these two conductors are connected, and that's the indication of short circuit here. So essentially, one of these conductors is connected to one conductor of the coaxial cable, the other one is connected to the other one, and they're now connected to each other. So that makes a loop antenna. So as you see, we are getting a short-circuited transmission line, and then we convert it into a loop antenna as shown here. Now, why this should work? So this is one question that you might have, and to answer this question, we're gonna start by maybe a larger loop in the beginning, and then I'm gonna go to a smaller loop so that you can understand what's happening with the loop antenna. So if I have a transmission line like this, remember these are extremely close. And then what would be the current on this transmission line? So this is a short circuit. You're gonna get a large current, and this would be your current distribution, for example. And then you get exactly the opposite one here. So now if I take, for example, this to be in this direction, and that's going to give me so this is going to give me half a wavelength. This one would be in opposite direction. So this one is in this direction, this one in the opposite direction. And then on the bottom one, we have exactly the opposite. So this is going to be the current distribution of my transmission line. Because they are so close to each other, this cancels this cancels this. And then you get no radiation from your transmission line. But now let's take this point, point A, let's take this point, point B, and make a loop. So this is going to be your point A, this is going to be your point B. Now I'm plotting them close to each other. So now I'm going to have a loop like this. So that's going to be my loop. And essentially these 2 points are the same point. They're connected to each other and they're very close. Now this would be my current distribution. This part becomes this part becomes this part becomes this part, and then this part becomes this part. So this is going to be the current distribution on my loop. And so this part, essentially, I'm treating it as 1 point because they're very close. And let's call this maybe C. Let's call this D. This is your point C. This is your point D. And you may call the whole thing here, for example, E. This point is point E. So that would be my current distribution. Now, if you look at your current distribution, and then I ask you, okay, what do you see when you are looking from here? So when you are looking at the whiteboard, or this is the axis of the dipole. So when you are on the axis of the dipole, very far from this loop antenna, what would you see for this loop antenna? So what you see could be something like that. So you may think of these 2 currents, this current and this current, as one dipole antenna. And then you might think of this piece of current and this piece of current as another dipole antenna. So when you are on this axis in the far field and you look at that, you might think of it this way. So now what do you have? When you are on the axis, you essentially see 2 dipole antenna that they are helping each other. So you're going to get lots of radiation when you are on this axis from the loop antenna. So this is very interesting because this short-circuited transmission line tend to cancel everything. This is going to cancel this, this is going to cancel this, but this one is actually, by this trick, it's now helping you to get maximum radiation when you are along the axis. So if, for example, if this is my antenna, and if this is the same size as this, and let's check the size of this, this was half a wavelength. This, therefore, is half a wavelength. This is so tiny because it's transmission line, so the total length would be this plus that. So this loop would be lambda loop, 1 wavelength loop. So if the length of this is 1 lambda, for example, if you are working at 1 gigahertz, if the circumference of this is 30 centimeter, which is 1 lambda, then all of a sudden you get very strong radiation toward you along this pen. So you see that with this simple trick, you can do interesting thing when it comes to loop antenna. So this particular example that I explained for you is 1 lambda loop antenna. You're going to see that in the video labs. This is part of LabVolt antenna training measurement system. And I'm actually going to measure this antenna for you. And I'm going to measure it in different shape, in the shape of circle and also in the shape of a square and one more. So you're going to see that in the videos of the lab as part of LabVolt training system. So, but my point here is that with this trick, you can actually go from no radiation to essentially 2 dipole all of a sudden with this loop antenna. So, but what I'm going to focus right now is not about this type of loop antenna. You're going to be learning about this in the lab. The one that I'm going to be focusing is a small loop antenna, which is not as nice as this one in the sense that this one is so nice because you convert it along this axis to almost 2 dipole antenna. So this is not as nice as this one, but it is a still important thing, and we're going to learn about that. So the one that I'm going to focus here is a small loop antenna. So a small is with respect to circumference. So the circumference here is 1 lambda. So this is not a small. So a small loop means circumference C less than lambda by 10. So we want to be a small compared to wavelengths. So this one, essentially, if I want to study this one, is not going to be like that. So I'm going to have my transmission line short-circuited. Then this is going to be my current distribution. So maximum here, then this is going to be my lambda by 4. This point is my lambda by 2. And if I want to be a small, I can only afford to get a small piece of this one. So I'm going to get from here to here. And I'm going to use this to make my loop. So if you do that, then when you make your loop, so this current would be based on that in this direction. So this is going to be your current. So this is going to go this way, and this is in this direction. So this is going to go this way, come back here, like that. This is like a standard loop that we know. So if you look at that, if you have some current going here and then coming back. So it's very consistent. The current goes here on the loop and come back exactly as you expect, for example, from a loop in basic electromagnetics when the current is DC, that it goes here and comes back. But remember, when the size of the loop is lambda, the current does more interesting thing. So if you look at this current distribution, is not intuitive based on what you've seen, for example, in terms of loop and a DC current. Remember, this is a AC current and it's a transmission line because the length is large with respect to wavelength. So you see this type of things that's not intuitive for you. But as soon as you make it a small, you get exactly what you expect from a loop. The current just goes like that, come back. So compare this current to this current, and you see that they are different. So this would be a small loop antenna where the circumference is small. Now, if you increase the circumference, you can use more of this. And as soon as you use more of this, you see now you have a current in this direction, but this side, the current is in the opposite direction. And that's why you get these interesting current distribution when you increase the circumference. Now, this is a small current, a small loop antenna. And we want to analyze this small loop antenna. But before analysis of this a small loop antenna, let's get an intuitive feeling about its radiation pattern. So let me start by getting some sort of intuitive idea about its radiation pattern. So let me first of all plot it larger so that we can see it better. But remember that I'm gonna assume that current is the current of a small loop. So the current goes this way, and then here, and then here, and then here. So this is essentially a small loop antenna for us. And you can see that based on the current distribution. So now I'm going to ask you, what would be the radiation along the axis? So toward you, essentially. Does it radiate toward you or not? So here you could be mistaken because I've shown you the 1 lambda circumference that it had maximum radiation in this direction. You might say, okay, this is going to have maximum radiation on the z-axis, which is toward you. But that's not true. That's not correct. In fact, this is exactly opposite. 1 lambda loop has a maximum radiation here because you've seen it as 2 dipole. But if you look at that, you can say the same thing for this, because even if you think of this as 2 dipole, these 2 dipoles tend to cancel the effect of each other. For example, look at it this way. You can think of it as 1 dipole if you want. Then this dipole here would be opposite. And because this is a small circumference, these would be extremely close to each other. So when you are here on the axis, these two dipoles exactly cancel the effect of each other. Whereas for the circumference of lambda, you get two dipoles in the same direction. So that's something to keep in mind, that you can't really, if you go by that, you also get the same, you get the result that in this direction, it cannot radiate, which is true. A small loop on the z-axis, on the axis of the loop, there is a null, in fact. So this is actually interesting that you get a null compared to the circumference lambda, which you get maximum radiation. The other way that you can think about this is based on the reception of the antenna. So remember, you're gonna hear this more in the video labs of the measurement, that we have reciprocity. So antenna transmit pattern and receive pattern are identical for essentially most of the antenna. So, what we have here, in this case, we could think of this antenna as receiving antenna, and then we say if it's gonna receive a wave that's coming this way, if it can receive the wave, then it also could transmit. So let's bring a wave in this direction to this antenna and see what's gonna happen. So to bring a wave, I'm gonna have EH going this way. So EH going this way. So this is my E, this is my H. They're traveling toward the antenna. So can this be received by the antenna? Can this be received by the antenna? So this is the question. So I want to emphasize that this is the direction of the magnetic field. This is the direction of the electric field. Can it receive it? So you can easily answer that based on what you've learned from basic electromagnetics, that a current like this generates a magnetic field in this direction. So look at my hand. So it generates a magnetic field in this direction. So essentially, this antenna, to receive something, it requires a magnetic field in this direction. Whereas if you come in this direction toward the loop antenna, remember, this is the direction of wave propagation, but the direction of magnetic field should be in this direction. This is your E, this is your H, they're traveling together. So this is the direction of electromagnetic wave. So this is the direction of B that's gonna interact with this loop, but this loop expects this magnetic field, so therefore it cannot receive any signal, and therefore there is no reception. You could say in the transmission, there would be null. And you could also justify it based on these two dipoles that are essentially exactly opposite when you look at. So this one, these two would be this, and these two would be this. So that's essentially the justification that there is no radiation here. Now, that essentially means if I work at a frequency that this loop is a small, let's say lambda by 10, then what's going to happen is that I'm not going to have any radiation toward you, so toward the axis of the loop. Whereas if the circumference is about one wavelength, in fact, I have maximum radiation toward you. So this is what we can learn from this loop antenna. Now, this is the null here. Now let's do another example, and now let's go around the loop. So essentially, assume that you are in the far field and you go around the loop and you want to observe what do you see. So let's say you are here and you are looking at the loop antenna. What do you see? So what you would see, I mean, this is not an exact thing. It's just I'm talking intuitive here. What you could argue is that you could see two dipole antenna, but these two dipole antenna essentially are separated a little bit from each other. So you see one dipole here, and you see another dipole here. So this dipole and this dipole. So this radiates, but they are very close. So they tend to cancel the effect of each other. But still, they're a little bit far from each other. Therefore, you get something. Still, you get something. And then if you go around, you could argue that with the same thing. For example, if you are here, you can think of these two currents as one dipole and these two currents as another set of dipole. And then you may argue that you have something like this. And therefore, because of this small distance, they don't cancel the effect of each other. But the thing is, when you go around, by the same argument, you can essentially say everywhere around sees the same thing, because all of them sees, for example, two dipole antenna a little bit separated, so they don't completely cancel the effect of each other. Therefore, you still get something, but then you get equally. Then at this point, you might object to me that you said in the axis you don't get anything, but in the axis, if I look, I still could see two dipole antenna separated a little bit. So why on the axis you said there is a null? I mean, although they are separated, let me, for example, plot it here. So this is one current, this is another current, and this is, let's say, this is the axis. So although they are separated, but when you are on the axis, the distance from the observation point to this antenna and the distance from the observation point to this antenna, it remains the same. So if they are exactly opposite to each other, they're going to cancel the effect of each other here. Whereas in this case, the distance from this point to the observation point is different from distance to the observation point. So they cannot completely cancel the effect of each other. So that's the difference. That's why on the axis, it's complete cancellation null, but when you go around, you still get something. Again, this is not exact analysis. It's just intuitive discussion about this antenna for better understanding it. So now, if I go by this logic, then I can say that if I have a loop antenna, and I need to correct myself, if I have a small loop antenna, and then z-axis would be toward you, the pattern of the antenna in the xy plane is in fact omnidirectional, because if I go around the antenna, I get the same thing. Now, what about, for example, xz plane? So this is my x, then z plane. So let me have my z and then x, and then this is going to be your pattern. You are still going to get this donut shape, because along the z-axis, you essentially receive nothing, and that's your null. But then on the x-axis, you get something. So this is going to be very similar to dipole antenna. Dipole exactly has that. So if this is my loop, and assuming that this loop is a small, and a small, it depends on the frequency. So you need to choose a frequency that is a small. Then if it's a small, along the axis, no radiation. If you go around, similar radiation, which would be this case over here. So that's the discussion on my small loop antenna based on this type of intuitive discussion. Now we get to equation, and we're going to observe the difference between this antenna and dipole antenna. And the difference here, although the patterns are the same, would be on the component of E. If you derive the electric field for dipole based on the coordinate that we had, you get E theta. In this case, if you derive it based on the same coordinate, xy here, then you get E phi. So you see that you go from E theta to E phi. In dipole, you had H phi. In this case, you're going to have H theta. And we're going to see that later. Thank you.